Let's get on with this last lesson. So this will be the last one that we'll do, like in general for the year. So this will be the last time you actually hear me, which is, I mean, sad for me, but you guys probably don't care as much. All right. So we're gonna be talking about electromagnetic waves and basically like the spectrum of colors and how that affects wavelength and frequency. So we first know everything you know about electromagnetic waves is that they are transverse waves. And they consist of changing electric and magnetic fields we talked a little bit about last lesson. The thing about these electromagnetic waves, okay, they carry energy from place to place, but not within the medium. So like whenever you see light, that carries energy from where it starts to where it ends, but it doesn't carry energy within the medium. An example of these electromagnetic waves are things like you've experienced almost every day, like radio waves, microwaves, infrared waves, visible light rays, X-rays, and gamma rays. Right? You experience all these at one point in your lives, whether you actually realize it or not. Now, since these are transverse waves, okay, they are different from mechanical waves in that electromagnetic waves are produced when an electric charge vibrates or accelerates compared to when mechanical waves didn't originate like that. Right? And electromagnetic waves do not require a medium, so they do not require anything to actually travel through. Okay, so electromagnetic waves can happen with or without a medium. They can have a medium, but it's not necessarily required. And then the last thing about with electromagnetic waves is they can also have electromagnetic radiation, which is the transfer of energy by those waves traveling through matter. So this is where now how radiation actually happens from electromagnetic waves is that when they travel through matter, so when they have maybe some sort of medium that's matter, okay, remember it has to be matter, we talked along like about beginning of the year, different types of matter. When it has that matter, then it usually has electromagnetic radiation. Okay. So talking about radio waves, just real quick, how they're different from sound waves. Okay. Remember radio waves, okay, are what you get from when you like turn on your radio from like whether it's your car or like an actual portable radio, which none of you have anymore because that's so old. But remember, we talked about sound waves, like, and they are similar. But if radio waves were actually the same as sound waves, okay, you would hear everything when you walk outside, right? We know how sound waves travel, like the Doppler effect we talked about last time. But if radio waves behaved in that similar fashion, we'd hear all the stuff going on from every single station that would ever be on radio, whether it be FM or AM. Okay, so that's how they are different in that case, is that we don't hear radio waves compared to sound waves. So now we're going to talk a little about the speed of electromagnetic waves. Okay, all waves in a vacuum, okay, have the same speed, which is 3.8 times 10 to the 8th meters per second, which is the speed of light. Okay, but they can vary in wavelength and frequency. Okay, so this is the only two spots where they differ. Their speed is always the same, but their wavelength and frequency can differ. Okay, like we talked about before, your wave speeds will go to your wavelength and frequency. So if this is constant, your speed, okay, these two will change. Remember, for example, if your wavelength goes down, your frequency has to go up. Same thing and vice versa. If your wavelength goes up, your frequency has to go down for the speed to be constant. Okay. I remember talking about some waves. If we had a wave that had a very long wavelength, okay, then it had a low frequency, which gives off a low energy, compared to a wave that has a very small wavelength. Okay, it has a very high frequency, which means it has a very high energy. So looking at the spectrum now a little bit, okay, you've all have seen this in some shape or form, okay? You have gamma rays on the far left, which have a very short wavelength. So over here, we have a short lambda. And while you go all the way to the right, radios have the longest wavelength. Okay? And right here is where the things you only see in your spectrum, the visible light spectrum. So those are the only things we actually see with our eyes. Everything else we actually don't see. But as you see, wavelength, remember we just mentioned, can affect the wavelength, where gamma rays that have the shortest wavelength have the highest frequency and the highest energy. And as you keep going to the right, as your wavelength becomes longer and longer, you have a lower frequency and a lower energy. So it's important you understand the relationship between how wavelength, frequency, and energy are to each other. As the longer the wavelength gets, the lower the frequency and the lower the energy, because of the speed being the same. So remember, going back to, I know maybe you might hear my phone ring, but the speed, remember, it always goes back to this equation, is equal to the wavelength times the frequency. Okay, this has to stay constant, and these two will change to keep the speed constant in this case. Right. This will be important too on your test. You should be able to recognize about where each of these things are on the spectrum. All right, now the long-awaited thing, when is light a wave or a particle? Right? You might have heard this at some point or shape or the other. Maybe in, I don't know, 8th grade science or something like that. But this has been a long debated thing. So let's see how light can behave as a wave or a particle. So electromagnetic radiation, okay, like the radiation that goes through matter, remember, like we just talked about, or the waves that go through matter, okay, behaves like a wave and a stream of particles at the same time. For example, okay, if you shine a light through one slit, okay, the light from the single slit produces the light coherently at the second one, right? So then it goes and you see the light being projected here, okay? But then once you have a card with two slits where that goes, okay, now you see interference going on. Okay, what the interference means is you have bands of light and dark light showing here. So like you have like this light band here, you have a dark band, you have a light band, you have a dark band, right? So you see parts of where light is shining through, okay? That relates how light can behave as a wave then, okay? Because you have an interference pattern going on, okay? So if you ever seen something that has like an interference pattern where you have bands of light and dark, that means that specific particle is behaving like a wave. And this is what interference deals with. So when we talk about interference, okay, on that thing behaving as a wave, okay, this is why. Because when you have two types of interference, you have a constructive interference and you have a destructive interference. Okay, the constructive interference, okay, is when you have two waves of the same that are added together. When you have two waves of the same amplitude, wavelength, and frequency all together, they double up. So you see now the amplitude gets double the size right now, but the wavelength will stay the same, okay? So wavelength will stay the same between these two in constructive interference, but the amplitude is what gets bigger. So constructive means they add together, they become a bigger wave. While destructive is when you have waves of the opposite. So if you see this wave starts up high, this one starts low, and then they behave in the opposite fashion. That means they'll cancel each other out, because you see, if this amplitude, let's say, is a positive 2, but this amplitude is a negative 2, right? You add them together, they zero out, which is what happens then. You have nothing going on. So these are what you see in the light bands, or the constructive interference, while the destructive and deconstructive interference are the dark bands. Okay? So this is what happens when you see that type of pattern occurring when you shine light through those slits. And then next is the particle example, so how light can behave as a particle. Okay? And this is with the photoelectric effect. And what the photoelectric effect states is that the emission of electrons from a metal caused by light striking the metal means light is a particle. So what that means is Einstein proposed that way back when he was still alive, was that all electromagnetic radiation consists of packets of energy called photons, okay? And these photons release energy, okay, that is proportional to light, okay? So these emissions from the electrons, okay, from a metal, okay, This is what causes light to actually happen. So if you remember way back when we talked about um, orbital notation in chemistry, okay, where electrons were here, basically, right? This is what's happening now. You have electrons being emitted from a nucleus, from an atom, okay, and those electrons emitting are jumping levels essentially. So like if this was like the 3 level and this is the 4 level and this electron jumps up here, it will release energy, and that energy will behave as light, okay? And that's where we can look at as how light behaves as a particle, okay? Because these energies being released are photons, which create light. So going back to that, those photons being released, okay, they have energy proportional to the frequency of light. So like for example, like if you look at blue and red light, blue light has a higher frequency than red light, which means blue light photons will have a higher energy than red photons, okay? So the higher the frequency, okay, the more energy that they will have in those photons. And going back to a little bit more about red and blue light and how they differ, okay? So if you shine, let's say, a bright red light at a metal, okay? The red light has less energy, remember, than the blue light. So remember, this has less energy, like we just talked about, and this has more energy. So because this red light has less energy than the blue light, okay, electrons won't be emitted as much, right? Because there's not as much energy to make those electrons start jumping around and start being emitted. But since blue light has more energy now, okay, that's what will cause these electrons to bounce off, because now it gives the electrons more energy. All right, it's like if you didn't have as much caffeine in your morning as you wanted to, you're not going to be doing anything right there. But when you have your caffeine, you're going to be jumping around, have more energy to actually do things. All right. All right, lastly, we'll talk about the intensity of light. So intensity relates to the rate at which a wave's energy flows through a given area. Okay? So if the intensity of light decreases, let's say, photons will travel farther from their source. Okay? What I mean by that is, like, say, like you have a spray can, okay? Same color, you have distance from the wall. So like, let's say this distance is 1 meter from the wall. This distance is, let's say, 5 meters from the wall. Okay? The farther you are away, right, when you spray that can on the wall, the less the lighter the color will appear, because you don't have as much, you have more surface area where the color is shooting at, so it doesn't appear as dark. While the closer you get, the darker it becomes, or the more intense the color becomes, because it's concentrated on a specific area. Light behaves the same way. Okay? So the farther the photons have to travel, the less intense they are. Okay? It's like when you get closer to a light, right? The closer you get to a light, the more like energy you feel, because in terms of like heat. But the farther you get away from the light, the less energy you feel. So that's the intensity. It's the same sort of thing. But the biggest thing with intensity is that the total energy does not increase. Okay? And if the total energy doesn't increase, the wave's intensity has to decrease then instead. Okay? So it's not the energy that's being decreased from here, it's the wave's intensity that's just decreasing. But that's pretty much it, in a nutshell, electromagnetic spectrum. Okay, so this will be the last lesson. I don't think I gave a homework assignment on this. Just watch the, if I did, make sure you look back at the lesson plans. If not, you'll basically have the lab, and then you'll have the test, and then you guys are done for the year. So if you have any questions, let me know.